Hi, my name is Gary Fox. I'm the department head and professor in the Department of Biological and Agricultural Engineering here at North Carolina State University. While we hear a lot about greenhouse gas production, especially from the burning of fossil fuels, managing the nitrogen cycle may have really just as much of an impact in terms of future sustainability. Biological engineers are uniquely positioned to address the grand challenge associated with managing the nitrogen cycle. What is unique about our department and about dealing with the nitrogen cycle is this idea that it integrates not only the chemistry of the earth, but also the biology of life. And that is whether we're looking at inputting nitrogen to grow food for a growing population to support what is anticipated to be 9.8 billion people on this planet by the year 2050, all the way into how we precisely apply that fertilizer in our crop field or in urban areas. Once we grow those crops and utilize those crops, we have to look at ways in which we are ensuring that the fertilizer inputs are going into that food production rather than running off into our streams and rivers or potentially polluting our groundwater. Again, once that food is produced, as waste gets generated, how can we make that process more efficient so that we're capturing the nutrients out of that waste, reusing those nutrients in a more sustainable way? And that's why, in my opinion, biological engineers are at the forefront of this grand challenge of engineering. The opportunity to connect the chemistry and the biology to address the nitrogen cycle. And in biological engineering at NC State, we have faculty, professionals, and researchers that are addressing each of these challenges from a variety of perspectives and allowing them to work with multidisciplinary researchers from across campus. Whether that's somebody that's using UAVs and drones and robotics to look at how to precisely apply this nitrogen fertilizer, to people looking at once that nitrogen fertilizer is applied, how to make sure that the plants that we want to grow, whether that's plants for food production or even plants for bioenergy, are using that nitrogen in the most effective way so that it doesn't run off. We also have faculty that are working in the area of animal waste management and waste treatment. How do we use technologies like anaerobic digestion to make sure that we're capturing those nutrients and potentially producing new byproducts that could be used as additional fertilizer materials or as additional beneficial uses in other applications. Our students are at the forefront of participating in graduate and undergraduate research opportunities right now on this grand challenge. And one of the things that we in biological engineering very much promote is a hands-on education, all directed at trying to make all of these linkages and processes that you've heard about in terms of the nitrogen cycle more efficient for the use of that nitrogen.
In terms of the nitrogen cycle, precision ag plays a part in making sure we put the right products at the right rate, at the right place, at the right time onto the field. So we do that in a way that gives the plant just what it needs, but it doesn't create excess nitrogen in the environment. We want to make sure then that once that nitrogen is put out, that we can extract as much value as possible from the crop and to limit that impact on the land on which that crop was made. We sense what the crop needs using different types of imagery and UAV systems, or we can also use existing sources of data, whether that's previous yields, soils maps, GPS data that describes what was done previously in that field. So whenever all that comes together, what we hope to do is to put just the right amount of nitrogen to the crop so that it grows fully and we get as much fiscal sustainability and environmental sustainability as possible. So BAE is equipped to deal with this particular grand challenge because we do stand at the face between, in my case, engineering and agriculture, production agriculture. So there's a lot of open questions about how do we optimize this system, but a lot of those are based on the engineered machines, the technology, the sensors, all these things that come together under this idea of precision agriculture or digital agriculture. And that's really driven by work that happens here in the BAE department and the way that we can ground truth it and real world it here in the field. So what we're doing here today in the field is that we're flying our drone with different payloads where we try to sense damage that has occurred to that crop. So if we've invested nitrogen into growing this plant, we want to make sure that the grower can harvest it and that it has value to them. So once the investment is made, we need to see the return. In North Carolina, harvest season tends to line up with some severe weather, that can be caused by hurricanes. One of the things we're trying to do is to assess if we can find that damage in the field and rate its severity. And the goal there being to create reports very quickly that allow that producer to decide if they want to harvest or make an insurance claim or whatever kind of their down the road decision is, or maybe they need to report that to a disaster response agency. So what we're trying to do is to create a data set that will allow us to train some machine learning models that will automatically identify what has happened in this field in terms of damage. Now that could be weather, that could be wildlife damage, that could be any number of things that would cause the crop itself to damage and to not create value for the grower for the inputs that were put in on it.
Hello, my name is François Biagan. I'm a professor here in Bio and Ag Engineering. I work on water quality issues, particularly on the excess nitrogen problem. I've always been passionate about ways to improve water quality. Turns out that there are several ways we could improve water quality, particularly improve the amount of nitrate that go to our waterways, actually lower them. And it turns out that there are in nature true natural filters that will take nitrate out. What we're trying to do in part of my research is take the idea that exists in nature and apply it and try to improve it, optimize the system so that it works even better than nature would do normally. And so one of these big ways of removing nitrate, to put water that contains nitrate through filters, one of which is what we call wood chip bioreactors. It's essentially a big soil pit in the soil that we fill with wood chips. It contains carbon, which is the source of energy, and the source of energy is taken by the microbes, which use the nitrate to actually and transform the nitrate into a gaseous form. So the nitrate that was in the water actually leaves the system into the atmosphere. The problem with this system is that it's efficient for a short period of time, not too long. So we're trying to find ways to really make it good again and again and again. And to do this, we essentially give the microbes that live inside the wood chip pits a breather. So this is a lab experiment to try to test different conditions or different effects in control conditions. And so what this is here, we have columns that are filled with wood chips from here to here, and we actually pump water. That's the little noise that you hear. We're pumping water through the column upward, and once it gets all the way up here, it just flows here to waste. And above here we have an airspace because we're trying to also measure the gaseous emissions as much as the effect on water quality. We've been able to find that it has a huge impact on the ability of that filter to filter the nitrate. What is it that we're doing that's different, that's new, that's really fascinating? We're sampling that water so often, every hour for each column. We're analyzing it automatically with this instrument here. We've built an auto sampler here in this department using controls, things that you learn as engineers, and we've applied them for a very live application, for water quality application. And so what we've obtained is that instead of having just several points, we've had hundreds, thousands of points, of data points, which allow us to really understand so much better how everything functions in these systems. So as part of this research and as part of this project, we get to work with world-class researchers and world-class equipment. This equipment here, which looks like a true black box, it's actually a laser system that measures the nitrous oxide in air in each of the columns there. And so we're able to measure the concentrations every second. This is what we do in this department. We actually work with world-class stuff to obtain, I think, world-class results.
This is Dr. Minjian Wang Li, and a professor in the Biological and Agricultural Engineering Department. And by now you have heard about the nitrogen cycle. And my research team is also doing some work on the ammonia emission, which is a very important part of a nitrogen cycle. And first of all, ammonia on one hand, it is a good thing. It can promote the crop growth if used as a fertilizer, but excessive atmospherical ammonia could generate a large-scale environmental concerns. As you can see, atmospheric ammonia, once emitted, and it can react with acidic gas to form a secondary aerosol and compromises the air quality. Ammonia has rapid deposition properties. Once you deposit it onto the Earth's surface, if it's onto the water, it can cause water eutrophication, and onto the soil can cause soil acidification. 80% of the atmospheric ammonia comes from the animal production, and more specifically from food animal housing environment systems. And research has been focused on the quantified emission from those facilities. Feed, transport, and the transformation of ammonia from animal production has not been well studied and understood. So our team has been working in this area to fill up the knowledge gap. One of the tools we're going to use to quantify the air surface exchange of the ammonia and the ammonia ions. And this tower we're going to use to collect the field data to do that, to get the concentration gradient, to understand the deposition or the emission of the ammonia. In the Biological and Ag Engineering Department, we do have a one-of-a-kind poultry engineering chamber systems which allow us to do a controlled study of the mechanisms on the emission generation and the emission of the ammonia along with other polluting gases and particulate matter. And you actually are at the site of our chamber facility. We do have a controlled system with a computer and the software and the controller, PLC controller, to collect the online data on the ventilation rate and the thermal conditions and some other parameters. This system is well controlled and also allow us to do not only the air emission study but also animal welfare and animal housing environmental control study. The unique part of this system is to provide the student the opportunity has the hands-on not only on the fluid dynamics, thermodynamics, but also electronics and the controls.
My work focuses in animal waste management in trying to recover nitrogen and phosphorus, keep them off of the fields in the first place, try to concentrate them and put them in places where they're back in the feed cycle. One way I do that in a particular project is to use separated liquid from swine manure, from pigs. That liquid is going to contain large amounts of urea and ammonia. And if we can preserve that material, we have a good fertilizer. And we've been able to do that. What we have to do is remove the water, because that is still 99% water, and that's very expensive to transport. So a project that we're doing right now is trying to concentrate that by at least 90%, to remove 90% of the water through vacuum evaporation process. This is an industrial process that's used throughout Europe and the United States for various operations. And we're trying to apply it to the concentration of this waste material and convert that into a useful product. Biological engineers are very useful in this because they understand both the physics and chemistry of how this system works, as well as the biology, plant biology, microbiology of how the product would be used, so we can understand how to do the collection, the processing, and what it means to actually use the product on an agricultural field in an ag setting. And the students that are working on that are getting their hands actually on this equipment, and they're helping in the research lab, taking measurements, helping set up experiments. They'll be in the field helping collect samples and record data. They're getting a first-hand experience of how this actually works and how it can be useful.
My research mostly looks into agricultural systems and the waste generated from agricultural systems, livestock production and crop production. Currently, the management systems that are used to use these wastes primarily go towards recycling on agricultural fields are not always very precise, and that results in an increased losses of nitrogen to the environment. So there are losses of the nitrogen that has been produced primarily for food production, which is an economic loss, but then that losses of the nitrogen to the environment results in air and water quality challenges. So my work really tries to close that gap by improving that recycling use. In animal waste recycling processing, there are different technologies, biological systems, thermal and mechanical systems. Examples of that could be liquid-solid separation using particle size distribution. The goal of that work is to improve the distribution of these nutrients between the destinations where they will be used and the origin where they came from. One of the key challenges facing agriculture in recycling nutrients, nitrogen in particular, is the economies of these systems. Most of the systems that currently exist are geared towards larger scale, municipal scale, similar to wastewater treatment, without a very much attention to agricultural scales in terms of individual farm or group of farms. So my research really looks into combining this technical innovation and the economic models to try to look for an adoption model and implementation that can improve the nitrogen use and recycling. So I recently worked on a project that was jointly funded by the National Science Foundation and the U.S. Department of Ag to develop a framework, a market framework to improve the management of organic waste across different sources. Primarily, this work looked into analyzing the sources of organic waste with the full attention to nitrogen from agriculture, from urban or municipal, as well as from industrial sources, and look into developing a market similar to the utility or electricity markets, where the sources, processors, transportation, infrastructure can all come together and to provide these services. So markets generally are organized around the economics. That none of the players in any market stand to lose money. So by adopting this model, we can actually look to the value-added aspect of nutrient recycling and looking for the places where this recycled stream of nutrients, nitrogen in particular, can be useful. We started by developing a case study for a particular agricultural watershed in Wisconsin and looking into the sources of nitrogen, typically food production systems like dairy systems, also industrial processing, and household waste. Combining with that water management or utilities, and combining all of these sources and looking into different technologies, solid liquid separation. We looked into precipitation of the nutrients, nitrogen and phosphorus, in a struvite format. We looked into composting. We looked into a suite of these technologies and started to assess what is the potential of each of these technologies to adjust the nutrient imbalance in that particular area. To my mind, agricultural engineers work in this really interesting interdisciplinary space. So on the one hand, they are involved with large essential systems to human survival. They are involved with food production, which is the primary user of nitrogen as a resource. They're directly involved with the water systems, which typically are the fate for a lot of the nitrogen. Their skill set involved using engineering principles and engineered systems to manage nitrogen, to improve food production efficiency, to improve recycling of these nutrients, upgrading of the byproducts. The agricultural engineers receive training across multiple scales, from modeling microorganisms on the cellular level to simulating river basins and watersheds. All of that helps the agricultural engineer understand the scale of the challenge and use the different engineering tools in our toolkit to approach it. In my research and my colleagues, we use economic, we used technical, we use spatial analysis, and we use modeling, we use sampling and field data collection. And we have access to agricultural sampling sites across the US to validate our observations and to develop more sustainable systems for using nitrogen as a resource. So to my mind, biological and agricultural engineering is the department primed to deal with this challenge.
So in biological engineering at NC State University, we are really at the forefront of addressing this grand challenge associated with managing the nitrogen cycle. You can really use your engineering fundamentals, those fundamental principles that you will learn about in terms of mass balances and energy balances are really at what drives this global nitrogen cycle.